Hello, welcome back to our second talk of today. So now we're going to listen to Andrés Chirre from Pontificia, Universidad Católica del Perú, and he's going to speak on remarks. His talk's called Remarks on a Formula of Ramanujan.
Okay, hi, can you hear me? Right? Okay, thank you so much, Ramon. Firstly, I would like to say thank you so much for the organizers. It's very nice to have something like that here in South America. Thank you so much. And thank you so much, Felipe. Felipe Gonzalez sent me the invitation some months ago. Felipe is my academic brother, my collaborator, and also, he don't know, but he's my best friend also. So thank you so much, Felipe. Okay, let's, before to start talking about this part, let me talk a bit about what Marco mentioned yesterday. I was a student at IMPA also 5 years ago, and really it's a pleasure give a talk here in Ricardo Mañé Auditorium. It's like a dream for a PhD student at IMPA. So I am very happy for that. To put an evidence, this is a photo when I defended my thesis. Here is the people, and Gugu is also here. Gugu, hi Gugu. Also here, and the other professor at IMPA, Professor Dimitar Dimitrov, and Andrés Chirre, me, Professor Felipe, Professor Mikhail Belopetesky. Okay, I don't want to cry, so let's talk about mathematics. Let's go. Okay, this beautiful object, right? I suppose that you love that. The Riemann zeta function, right? It's amazing. We learned in a classical course of analytic number theory that this is a beautiful series. This is absolutely convergent when the real part of S is bigger than 1. And you can define an analytic function on real part is bigger than 1, right? Something that also you learned in that course is that you can extend this function as a meromorphic function, in fact, for the whole complex plane. So this is an analytic function on C, but not at point 1, because at the point 1 you have something called a pole, right? Pole as residus 1, really, a simple pole. And this is something that is very interesting in analytic number theory, because we have an analytic function and we would like to understand what are the zeros of that function. And you learned in a course of number theory, okay, that here you don't have zeros, right? Because it's a product of things that are not zeros. You don't have zeros here essentially. On the left-hand side, real part is less than 0. What you have something called trivial zeros. Trivial in the sense that we know the zeros, -2, -4, -6, blah, 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 blah. And the question is about where are the zeros in this part here, the critical strip, right? This is one of the dreams in analytic number theory. Of course, I believe in the Riemann hypothesis. I suppose that, or I hope that you also believe, right? Felipe, do you believe or not? Oh, Felipe. Okay, where are the other zeros on the critical strip? And as I mentioned to you, there is this conjecture, the Riemann hypothesis, that say that all the zeros that are on this critical strip has the form 1/2 plus I gamma, where gamma is a real number, right? This is the famous Riemann hypothesis related with the zeros. And this is our friend Riemann. What we know about the zeros now, about the zeros in the critical strip? Well, you can find the first zeros in the sense of height here, and you find that the first zeros is 1/2 plus 14.13 blah, 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 I. So perfect, the Riemann hypothesis in the first point. If you go more, you can find the next zero, 1/2 plus 21.02 blah, 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 I. Nice, 2 zeros, but we need to find more zeros. And you continue with this idea, and really you can prove until now that all the zeros that have imaginary part less than 3.10 power 12 are on the critical line. So this is a partial Riemann hypothesis until now. We have until this level, but of course we don't have the other level also, so it is an open problem until now. Okay, but related with the Riemann zeta function appeared this arithmetic function, the Mobius function, mu n, defined in the following way. You pick a natural number and you factorize this natural number, and therefore if the factorization has different zeros, Therefore, the mu n is minus 1 power the number of the different zeros. If not, you put 0, and we are happy about that. Mu1 is 1 is 1. Or mu1 is 1. And therefore, you have this function, this Mobius function. What is the relationship between the Mobius function and the Riemann zeta function? Appear here. 1 over zeta is this series here. 1 over this series, 1 over n power s, is this series mu n over n power s. This is something that I consider something magic in number theory, that you can express 1 over zeta as this series here. And something that also you learn in a course of analytic number theory is that, for instance, the function zeta has a pole at the point 1, therefore essentially 1 over zeta has a 0 at the point 1. Therefore, you can prove really that this sum here, this sum here, when you put s equals 1, you can approximate to s equals 1. This guy here is 0. Okay, you can prove that. And we will call that the prime number theory in this talk. This is clear until now? All is clear? Okay. Who is this mathematician? It's a famous mathematician. I am sure that you have the book of this man in your library, in your house. Titchmarsh, Edward Charles Titchmarsh. I am sure that you have that book in your house, right? Titchmarsh had this beautiful book, The Theory of the Riemann zeta function, that I suppose that you have read one time in your life. This book has an interesting observation about the partial sum of the Mobius function. If you define mx as the sum of mu n when x running until x, therefore he writes this expression. The finite theory of mx is extremely obscure, and the results are not early so precise as the corresponding ones in the prime number problem. The best on result, blah, 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 and he starts talking about the function mx. This is one of the phrases I really like about the mysterious part of the partial sum of the Mobius function. And to be honest, the first time that I read or I heard about this phrase is not on Titchmarsh. Was looking on internet, and I found this conference here, this workshop. And Professor Steve Gonek also mentioned that phrase in the conference, reference to the Titchmarsh book about the mysteries of the function mx. So the work that I will talk today is a work with Professor Steve Gonek when I was postdoc at Rochester University. I spent 1 year there. And the history started in the following way. We have a lunch with Professor Gonek on Sunday. And then when we are returning to the university on Sunday, right? We are returning to the university on Sunday to continue working. Professor Gonek asked me, Andres, do you know the Ramanujan formula? I asked to you, do you know the Ramanujan formula? What is your first idea?
1 over 5?
Can be, yes. My first thing in my mind was, which Ramanujan formula? Right? And appeared in my mind this. El hombre que conocía el infinito, the man who knows the infinity, right? I suppose that you watched this film, right? Did you watch it? Have you watched this film? It's very, very nice. Please, try to watch this film. In this film, appears the history of Ramanujan, and there is a scene where Ramanujan is talking with Hardy and Littlewood. And they are excited because Ramanujan gives to them a book of the formulas that Ramanujan obtained in the past. And they are happy and they say, okay, we will spend 1 life to understand this formula. And Ramanujan said, well, maybe 2 lives. And appear another book, the second book of Ramanujan formulas. So when Professor Gonek asked to me about the Ramanujan formula, I was thinking there are infinity formulas in that book. So what formula you are talking to me? In my mind appeared that, and I remember, oh, Professor Gonek loves the Mobius function. So maybe it's a Ramanujan formula related with the Mobius function. And I respond to Professor Gonek, maybe you are asking me about this formula here. The sum of mu n over n you fix b bigger than 0. This exponential here, the Gauss, the exponential here, sorry, this. The exponential minus b power 2 over n power 2 minus this root pi over b, and this series is equal 0. This is a formula that Ramanujan wrote in one of his books, okay? If you watch the video, the film, you can see that Ramanujan never say how he proved that. He only say, this is the formula that we have. Okay, why 0? This is maybe the first question. After that Hardy and Littlewood, they tried to understand this sum, and they obtained the following formula. They didn't obtain 0. They obtained this sum here. That may be 0, I don't know. But they obtained this sum here. The sum over rho are the zeros of the Riemann zeta function. The gamma function here, 1 over 2 minus rho over 2, over zeta prime rho, the derivative of zeta, are the zeros of zeta, and pi over b power rho minus 1 over 2. Right? When you see this formula, what is the first question that you ask? You have a series, right? So it's convergent. Second question, you have 1 over zeta prime rho. So you are assuming something, right? So to see that to understand this sum, you need to assume that, for instance, that zeros of zeta are simple, because zeta prime of rho will be different to 0, right? And now, Hardy and Littlewood, they mentioned that there is a way where you can group the zeros such that you obtain that this series is convergent. But they never say how you can do that. Okay? This is the formula. And after that, Titchmarsh, in the book, well, in a paper, but later in the book, they say that there is, if this is possible to organize the zeros in the way that you can group together in this way, here, therefore you get convergence of this series here. Okay? This is something that appeared on Titchmarsh's book. Well, something that I would like to understand is this function here, this big guy here, this sum here. So let me call this guy here fb. For any b bigger than 0, I will define this series that in the beginning is an innocent series, right? Mu n over n and this exponential, this Gaussian there. Now, if you want to rephrase the Hardy and Littlewood formula, is this one. Root a fa minus root b fb is minus 1 over 2, and this sum where a and b are positive and the multiplication is pi. Okay? The first question is a series. I would like to be sure that this series is well defined. Well, this function fb is well defined because you write the exponential as 1 plus b of something when y is small, and you use the prime number theory that I mentioned to you. Therefore, this exponential here is 1 plus this guy here, b power 2 over n power 2, and you have this sum here. And as I mentioned to you, this sum here is 0. Therefore, you get this sum mu n over n power cube b power 2. You bound this mu n by 1. The sum 1 over n power cube is something bounded, and you have b power 2 here. Okay, this series is a well-defined series. This is not absolutely convergent, but has this function. Okay, and Hardy and Littlewood, they prove that the function fb is bounded in this way here. For any epsilon, there is a constant such that fb is bounded by b power minus 1 over 2 plus epsilon, and the constant in front there. And they prove that this is equivalent to the Riemann hypothesis. Okay? But they have a certain conjecture saying that, in fact, the function is fb is bounded by b power minus 1 over 2 without this epsilon there. Why we should believe in some sense that this is true? This is because, for instance, stats prove the other direction, extreme values of this function fb. He proved that fb, the maximum of fb in this short interval, is something like that. T minus 1 over 2, b minus 1 over 2, this is t. So there is a feeling that it's possible that this is the right bound for this function fb. Okay? This is clear until now? Okay. But, Professor, you were talking about the function mx. So let me talk about the function mx and the relationship with that. The function mx is the partial sum of the Mobius function. And also in the course of analytic number theory, you learn that mx is big O, x power 1 over 2 plus epsilon, that this is equivalent to the Riemann hypothesis, right? We learned that in a classical course of analytic number theory. How you prove that? That mx is this guy here, imply RH. How do you prove that? How you can prove that? Abel summation, right? So you start with this guy here. The part S is bigger than 1. So 1 over zeta S that you know that this sum here, mu n over n power s. You can use, as we would say, Abel summation, integration by parts, Riemann exchanges integration by parts. 1 minus infinity dmy over y power s, right? You evaluate on the extremal points, ny over y power s at 1 minus infinity, and you subtract 1 infinity, integration by parts, ny dy. When you take the derivative of this guy here, this minus blah, 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 over y s plus 1. Right? And you can prove easily, for instance, you can put the bound for mx, you can use this bound if you want, and this is easy to see that when you have real part s bigger than 1, this guy here, when you go to infinity, is going to 0, and when you go to 1 minus, you don't have nothing here, it's going to 0. Okay? Therefore, in the end, you have that 1 over zeta s on real part s bigger than 1. This guy here is this integral here. Right? And you conclude using this bound here. If ny is big O, or is bounded by a constant, y 1 over 2 plus epsilon, therefore here you put this, and it's defined an analytic function, right? In real part s bigger than 1 over 2. Right? And this implies that 1 over zeta is well defined in real part s bigger than 1 over 2, therefore you don't have zeros. In real part s bigger than 1 over 2 and less than 1. And therefore the zeros should be on the critical line. This is clear? Okay? Remembering analytic number theory. Beautiful. There is a conjecture related with mx called Mertens conjecture that say that mn is bounded by root n for any integer n. Okay? Unfortunately, it's not more a conjecture because this was disproved by Andrew Otelisko and Herman Dirail. Okay? So, there is another hypothesis that is something that the people usually also believe, that, okay, I don't have this, but I have this in average. Therefore, the weak-Mertens hypothesis establishes that you have that this integral mx over x power 2 is bounded by log x. Okay? Again, if you assume that mx is bounded by root x, therefore root x over x is 1 over root x, power 2 is 1 over x, the integral is log x. So this is like this is a weak hypothesis there. Okay? So in this talk, I will assume the weak Mertens hypothesis. Okay? But what consequence do you have if you assume the weak Mertens hypothesis? For instance, you have the Riemann hypothesis. Okay? And let me prove that here. Okay? Using exactly what we did here. So, I have this information about this mean value here. So let me define fx as the integral of 1 over x and y over y dy. Okay? Therefore, you want almost everywhere you have this guy here. Okay? If you want, you can send as distribution. Therefore, if you come here 1 over zeta is s the integral of 1 to infinity. And therefore, you can write as a distribution the fy over y power s, right? Because the factor y power 1 to catch here. Therefore, I have this. I can use again iteration by parts. Therefore, you have this, this, from 1 to infinity, minus the integral here, 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 and the derivative of this guy here, that again is this with plus now, over s, y, s plus 1 dy. Okay? As in the past, you can bound this fy easily if you want to bound this guy here by, or x if you want, doesn't matter because now we are thinking when the real part is bigger than 1. Therefore, as before, this guy here is going to 0, and therefore you got this expression here. The other s is power 2. Okay? And as before, I would like to prove that this is an analytic function on real part is bigger than 1 over 2. And therefore, I would like to have a bound for fy. And this is something that you have using that, because using Cauchy-Schwarz, you have that fx is bounded by that integral here, power 2, multiply power 1 over 2, sorry, multiply the integral of 1 over 2. I am saying that fx is bounded by x, this is x, power 1 over 2, and you have here a log x power 1 over 2. Therefore, you have something like x 1 over 2 plus epsilon. You have here x power s plus 1. If real part s is bigger than 1 over 2, therefore this integral is absolutely integrable. Therefore, as before, you have an analytic function on real part s bigger than 1 over 2. Therefore, 1 over zeta again has no zeros there. Therefore, the Riemann hypothesis is true. We proved the Riemann hypothesis. Is clear? Okay, beautiful. Something more that you can obtain if you assume the weak Mertens hypothesis is the fact that all the zeros are simple. Okay, you can find that in the Titchmarsh book also. Other thing that you can obtain is that you have a bound for 1 over zeta prime rho. You have this type of bound. In particular, you can obtain the bound 1 over zeta prime rho is bounded by a constant, the modulus of rho. Another consequence of the weak Mertens hypothesis is that you have this gap between consecutive zeros of zeta. Okay? This for information A, B, C, and D, we will remember in our mind, please, because we will use this machinery now. If you assume weak Mertens hypothesis. So let's explore now the Ramanujan formula using the weak Mertens hypothesis. Okay? So remember that we have this formula here, right? And now, because B say that the zeros are simple, therefore now this expression has sense. This fraction has sense. Beautiful. Second thing, because the Riemann hypothesis holds, you can write rho as 1 over 2 plus I gamma. Next, Titchmarsh showed that there is a way that you can group the zeros such that this series is convergent. But if you assume weak Mertens hypothesis, you have more. Even more. If you assume weak Mertens hypothesis, you have this gap over the zeros. Therefore, the way that the Titchmarsh mentioned about a group the zeros is impossible. Okay? Let me say more. Now that we know that the zeros of zeta has the form 1 over 2 plus I gamma, therefore I can reorganize this sum here. I can reorganize my sum here, and therefore you move a bit, and therefore you obtain this sum here, considering only the sum when gamma is positive. Okay? It's just organizing the things. Now, we have C. What says C? C say that you have a bound for 1 over zeta prime rho. I can use this bound here now, okay? And to bound gamma, I can use the ceiling formula. Therefore, what you get that this sum here, this guy here, if you assume Riemann hypothesis rho is 1 over 2 plus I gamma, therefore the modulus of B power I gamma is 1, you have this sum here, you use a Stirling formula, you use the bound for 1 over zeta prime rho, and therefore you have this series that this is completely integrable, absolutely integrable. You have a good decay here. Essentially, what we are saying that if you assume weak Mertens hypothesis, therefore, this sum here is absolutely convergent. Okay? Now, let me return here. So let me call A B, and B, remember that is pi over A. You move to the other side, and I can rewrite this expression in this way, okay, without problems. And now remember that when we define the function fb, we prove that fb is big O b power 2, when b is bigger than something. Therefore, in particular, when b is small. Blah, 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 blah. Therefore, I have this guy here now, and because b is, assume that b is bigger than pi, so this guy here is less than 1, therefore you have a decay for this f pi over b. So this should be something like constant over b power 2. And you have this b, therefore you have 1 over b power cube. Essentially, we are proving that fb you can write in this way. fb is 1 over root b, multiply the real part of this series here, plus the error term. And what implies that? This implies that if you assume weak Mertens hypothesis, therefore when b is big, you have that. You can bound fb in this way here. How? Well, you take modulus. Here, you put a modulus inside. Maybe you lose a lot of information, but in the end you have a series that we know that is absolutely convergent. Right? Therefore, in the end you have this expression. fb is bounded by a constant. The constant is this series there over root b plus the error term. And if you pay attention, this is the Hardy-Analytic conjecture, right? Because they say that fb is bounded by b power minus 1 over 2. So this implies the Hardy-Analytic conjecture. Okay? Okay. We have this beautiful C also. We will investigate more about this C later. Okay? It's a series that should be a number, right? Because assuming weak Mertens hypothesis, we have that this guy here is absolutely convergent. So this is a number now. Even more, if you assume, for instance, conjectures like the linear independence hypothesis, okay, you can prove more about the function fb. Assume weak Mertens hypothesis a linear independence hypothesis, therefore, root bfb is dense in this interval minus cc. Okay, where c is this number, this series here. Okay? What is this c? This value of this c. Okay, how you can do? Okay, I have the zeros, so let me find the information of the zeros of zeta that you can find, for instance, in libraries on Google, blah, blah, blah. You find the zeros, and therefore, for instance, if you put gamma 1, the first zero, 1.14.21, blah, 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 I, therefore, you put here on gamma and zeta prime, you run the computer, and you get this number here. If you put gamma 2, you get this number here. Gamma 3, gamma 4, gamma 5, and blah, 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 blah. So if you continue with the list of zeros, you can see the appear a power 10, power something, minus, minus, bigger, 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 bigger. So we have the feeling in our heart that maybe the main part of this guy here is gamma 1. With gamma 2 if you want. Okay? Therefore, we believe that this series here, remember, we're assuming the weak Mertens hypothesis. This implies that this series exists, it's a number. And we believe that this number here is 0.000029314, blah, blah, blah. Okay? Again, why we believe that? Because we are assuming that gamma 1, gamma 2 has this behavior, but really we don't know about what happened with gamma, I don't know, 10 billion of billions. We don't know. But we believe that all the times are going to zero very fast with this size. Okay, so using the previous result that I mentioned, we prove that root BFB is dense in minus CC. And C is this number that I showed to you, 0.00029, blah, blah, blah. Okay, but to be honest, FB is a sum of mu n over n power n exponential, right? Multiplied exponential. Therefore, I can put this sum in the computer and do the graphic of this sum. and see what happens. Well, if you put root BFB in the computer, you can see the graphic, and the graphic has this form here. This oscillation as expected, and you can see the highest value here, that is close to 0.00003. Okay, maybe 0.00002931444. Okay, so this is an evidence that maybe this is true, that the fact that the main term of this guy here is gamma 1 and gamma 2 also. Okay? Okay, also the last part that I would like to mention is that also exploring more about this function f(x), we compute the second moment of this guy here. So I assume the Wigg-Mertens hypothesis. Therefore, the second moment has this expression, a multiplied log x plus an error term below 1. And this a now is this number here, 1/2, and this series, but now the series has modulus power 2. Okay? How you can prove that? Well, if you write S in this way here, let me recall this guy here. Let me rename this guy here as A gamma. So you have this sum A gamma x power I gamma. Therefore, if you want to compute this guy here, using the Ramanujan formula and assuming the Wigg-Mertens hypothesis, we know that this guy here has this expression. Okay? You take power 2, you open this guy here. Beautiful. And now, using the fact that this guy here is absolutely convergent, really the main term here all the time is the real part of S power 2. This guy here and this guy here are error terms, big O1 and big O1. Okay? The real part is you can rewrite in this way here. Okay? If you write S plus conjugate of S over 2, power 2, you rewrite and you obtain that. Okay? And the main term between this guy here will be with modulus of S power 2, because S power 2 this integral, conjugate of S power 2 this integral, using the absolutely convergent, are error terms, or are going to be O1. Therefore, I would like to understand this guy here. Therefore, I have a sum. I open the sum power 2. I have the sum gamma, gamma prime, A gamma, the conjugate of A gamma. I organize when gamma is gamma prime, it means the diagonal. So this integral is log x. This is the reason that appears log x. Okay? Plus I have the other term here. So if you group, if you put modulus here, therefore you have the other term here. Okay? And the idea is to show that this guy here is bounded. But how we can do that? It's because remember that if you assume Wigg-Mertens hypothesis, you have a gap between the zeros. Therefore, I can bound this guy here using this type of expression. You use a Stirling formula because remember that A gamma has a gamma in the numerator, right? And therefore, you use a Stirling formula and you can prove that this guy here is bounded. And we got it. Okay? And in the end, you obtain the second moment of this function here. There are analogous results, for instance, of the Ramanujan formula, if you find on the literature. Rees, for instance, studied this function here that is similar, but you are considering on the denominator n power 2 instead of n. Okay? But Rees obtained the Ramanujan formula for this function here, px. Okay? And also, Agarwal, Garg, and Maggi, they prove a similar Ramanujan formula for this function here, where you replace the number 2 by any k bigger or equals 2. Okay? So in our paper with Professor Gondek, we can also obtain similar formulas, as I mentioned before. Okay? But now for the function px and the function pkx. Okay? Thank you so much for your attention.